All right, this is our challenge problem video on mutually exclusive events and the probability of A or B. And it's a tough one. Okay, so why don't you pause the video? I don't want to scare you away, but pause the video, go ahead and try this on your own and see if you can get it right, and then check back in, follow along. So now we're spinning the spinner that you might have seen in an earlier video. We're spinning it 3 times in a row. And let's assume that you want to land on 1 first, or land on 2 second, or land on the number 3 third in that sequence of 3 spins. What's the probability of this happening? Okay, so before we were looking for a 1, then a 2, then a 3. We had very rigid requirements for how to get a success. Now we just need one of those numbers to show up in its proper spot, or 2 numbers or all 3 to show up, but we have a much looser set of requirements here. So just to be clear on this, if we roll 3 numbers and if we spin 3 times, we get a 3, 2, 1, that counts as a success because of the 2 being in the second spot. If we get a 1, 2, 1, that counts as a success because either the 1 or the 2 are in the right spots, but it doesn't count as 2 successes. And then if we get a 3, 1, 2, that would count as a failure because none of the numbers are sort of in their correct spot, right? So what's the chance of getting a success? Okay, a 1 or a 2 or a 3 in their sort of proper spots. So this is hard because we don't have a formula for the probability of A or B or C. We've been working with a formula for probability of A or B, and I'm going to actually paste in an image of that formula for A or B or C. Okay? And I'm not going to ask that we use it. I'm basically wanting to show you how complex it is. Okay? So by the way, in set notation, this U means union, which is a synonym to or. And this upside down U means intersection, which is a synonym for and. Okay? So you can see some familiar stuff in here. We have to add the 3 probabilities together, but then we have to subtract off the three different sorts of and problems, right? A and B, A and C, and B and C. And then what's weird, we have to add on this kind of triple and problem, A and B and C. Okay, I want to show you a better way of doing that. Well, not a better way, but a different way that I think is easier to follow, easier to remember. Okay, so let's see if I can get this kind of out of the way here. Okay. So I want to find the probability of getting none of the numbers in sort of the right spot. Okay, so I am going to find the probability of the complement. Remember that line means complement. And then once I find that, I can just subtract it from 1 to find the probability of what we're actually looking for. Okay, so to be clear, let me make a quick copy here. Up here, I will find the complement, but our ultimate goal is down here to find the actual probability. Complement's pretty easy. Here, let's do it. So think about what the chance is of not getting any of the numbers in their right spot. That means we want all kind of failures. So that's the same as this. Probability of not A and not B and not C. And that's really easy to calculate. So what's the chance of not landing on a 1 in the first spot? It's 1 out of 2. Because that's our zone of not landing on 1, right? And then we're going to multiply. What's the chance of not landing on event B is a 2, on a 2 in the right spot? That's 3 out of 4. That's this whole zone right in here. Okay, 3 out of 4. And then the same for C. Easy multiplying across the top. easy multiplying across the bottom, I think. 2 times 4, that's 32, right? Okay, so 9 out of 32 is the chance of getting all failures. So then what's the chance of getting any successes, which is really what we're looking for? It's the complement to that. It's 1 minus 9 out of 32. We can get common denominators. And so that's going to equal 23 out of 32. So we could have done this crazy formula down here. We should have gotten the same thing, and I encourage you to actually try that. But this is a great example of how using complements can help you find some pretty complex probabilities in a pretty efficient way. That's a good place to stop right there.